Hello, this is Savitha. Welcome to the video on periodic table and periodicity. This chapter comes under the first semester chemistry BSc under inorganic. Under this chapter, we'll be learning the ionization enthalpy, successive ionization enthalpy, the factors affecting ionization enthalpy, application of ionization enthalpy and its variation in a group and in a period, and the explanation for the observed trends. Coming to the ionization potential, it is the energy which is needed to remove an electron from an isolated atom or a molecule. So, from a neutral gaseous atom, when an electron is removed, the amount of the energy that is required is defined as the ionization potential. So, the first ionization energy is the energy which is required to remove the most loosely held electron from 1 mole of gaseous atom to produce 1 mole of gaseous ion, each with a charge of +1, and this is represented as follows. From a neutral gaseous atom, when an electron is removed, it gets converted into a positive charge and an electron is removed. And this is illustrated by taking the example of a sodium. So this is a neutral gaseous atom and an electron is removed, and this is the amount of the ionization energy of plus 494 kilojoule per mole is the amount of the ionization energy to convert the sodium to sodium Na plus. And let us talk about in detail about the ionization enthalpy. It is defined as the amount of energy which is required to remove an electron from the outermost shell of an isolated gaseous neutral atom. And it can be represented by the simple equation. N represents the element in the gaseous neutral and ionization energy, an electron is removed and this is getting converted into a gaseous cation and an electron is liberated, and this is usually expressed in kilojoules per mole. The process of ionization is always endothermic and ionization enthalpy is always positive. This gives a direct measure of the ease with which an atom can change into a cation. Smaller the value of ionization enthalpy, it is easier for the neutral atom to change into a positive ion. Coming to the next, successive ionization enthalpy. The energy that is required to remove the first electron from an isolated gaseous atom is the first ionization enthalpy. In a similar way, when the energy required to remove the second electron from the positive ion is the second ionization enthalpy. And similarly, there can be a third and fourth ionization enthalpy. And when an electron has been removed from an atom, it becomes increasingly difficult to remove the second and subsequent electrons from the resulting positively charged ion. Hence, there is a gradual increase in the ionization enthalpy. So, in detail, let us understand what is the successive ionization enthalpy. Here, the amount of the energy which is required to remove the second electron from a positive cation is the second ionization enthalpy. And here, let us illustrate the successive ionization enthalpy by taking the example the sodium. So the neutral gaseous atom, we are removing the first electron and the amount of the energy required is the first ionization energy. And from such a positive cation, when the second electron is removed, it is the second ionization enthalpy. The same is also when the third electron is removed from a divalent cation. We call it to be the third ionization enthalpy. So when we look at the values, there is a gradual increase in the ionization enthalpy, and hence ionization energy 3 will be always greater than the second ionization, which in turn will be greater than the first ionization energy. And this can be explained as follows. And it has been found that the successive ionization enthalpy goes on increasing progressively because it becomes difficult to remove an electron from that is the successive electron. This is due to the fact that after the removal of the first electron, the number of electron decreases with the nuclear charge remains the same, and consequently the remaining electrons of the next will be tightly held by the nucleus, and it becomes difficult to remove the next electron, and hence the second ionization energy will be more than the first ionization energy, and the same is also true with the third ionization energy, which will be further greater than the second ionization energy. And coming to the factors which affect the ionization enthalpy. There are various factors which are going to influence the ionization enthalpy or the ionization energy. Let us look the first one, the effective nuclear charge. The greater the nuclear charge, more tightly the electrons are bound to the nucleus, and higher is the ionization enthalpy. This can be explained as follows. The force of attraction between the nucleus and the outermost electron increases with the increase in the nuclear charge. Thus, the greater the nuclear charge, the greater is the energy needed to pull out an electron from an atom. Hence, the ionization energy increases with increase in the nuclear charge. For example, when we compare the ionization energy of lithium and beryllium, the beryllium have a higher ionization energy. This is because of a higher nuclear charge on the beryllium as compared to the lithium, and hence to remove an electron from beryllium requires the greater ionization energy, and hence the greater the nuclear charge, the more tightly the electrons are bound to the nucleus, and hence there will be a higher ionization enthalpy. This is the first factor which is going to affect the ionization enthalpy. Coming to the second factor which influences the ionization energy is the atomic size. The ionization energy decreases with the increasing the size of the atom, or in other words, the larger the atom, the less tightly the outermost electrons are bound to the nucleus, and hence smaller is the ionization enthalpy. The larger the atomic size, the smaller is the ionization energy. The reason for this is that as the size of the atom increases, the outer electron lie farther away from the nucleus. Hence, according to the Coulomb's law, the attractive pull of the nucleus on the outer electron decreases, and it becomes easier to knock out an electron from the outermost shell of the atom. Hence, the ionization energy for a larger atom is smaller compared to the smaller atom. For example, when we compare the ionization energy of sodium and magnesium, magnesium has a larger first ionization energy. This is because the size of the atom, that is the sodium atom, is larger as compared to the magnesium, and hence the smaller the size, the smaller will be the first ionization energy as compared to the magnesium, which has the larger size, smaller size, and hence it has the higher ionization energy. Coming to the electronic configuration, the electronic configuration also influences the ionization energy or the ionization enthalpy. So, certain electronic configuration are more stable than the others. For example, half-filled or completely filled orbitals. So, if an atom has fully filled or exactly half-filled orbital in the valence shell, its ionization enthalpy is higher than the expected values. For example, when we take the beryllium and nitrogen here this beryllium as well as the nitrogen has completely filled s orbital, and hence the ionization energy for the beryllium will be slightly higher as also with the nitrogen, and hence when there is a half fill, the ionization energy is higher than the expected values. And this is also true with the other elements like magnesium and phosphorus in the third period have a higher ionization energy, and this is due to the extra stability of the fully completed s orbital in the beryllium and the magnesium, and half-filled orbital in the case of nitrogen and phosphorus. So, when we compare the ionization energy of nitrogen and oxygen, nitrogen has a little slightly higher ionization enthalpy compared to the oxygen. This is because of the half-filled p orbital. It is difficult to remove an electron from such an electronic configuration, and hence it experiences a higher ionization enthalpy as compared to the oxygen. And when we go for the noble gases, or which we commonly call as a inert gases, helium, neon, argon, krypton, xenon, and radon, and when we look at the electronic configuration, this atom have completely filled, that is ns2 and p6, the outer electronic configuration, which we call to be the octet configuration. So here, because of the completely filled orbitals, when we compare the ionization energy of this inert gas, the values are very high, and hence it becomes very difficult to remove an electron from a noble gases or inert gases, and hence they are highly stable. So this is about the neutral gaseous atom. So when we take the lithium, when we remove one electron from the lithium and get converted to Li plus, here it once again gets the completely filled s orbital, and hence the second ionization energy for such a thing will be higher, and it is about 7292 kilojoules per mole. So whenever the atoms, neutral atom or ionic, have fully filled or exactly off filled orbital in their valence shell, its ionization enthalpy will be higher. Coming to the number of electrons that are present in the inner shell. The larger the number of electrons in the inner shell, the smaller is the ionization enthalpy. The electrons in the inner shell exerts the shielding effect on the electrons in the outermost shell. As a result, the outer electron experience the less attraction from the nucleus, and they can be removed easily. So the larger the number of electrons in the inner shell, the smaller is the ionization energy. The electrons in the inner shell act as a screen or shield between the nucleus and the outermost electrons, and this is known as screening effect or shielding effect. The larger the number of electrons in the inner shell, the greater will be the screening effect. Consequently, the electrons in the valence shell experience the less attraction from the nucleus, and hence the ionization energy would be low. So, the inner shells of the electron repels the outer shell electron, and they also form a shield, which we call them to be the electron shielding or the screening. So, the more the inner shell, the larger the screening and smaller the nuclear attraction of outer electron, and hence ionization energy is low. So let us take the example of hydrogen, helium and lithium. When we take the ionization enthalpy for the helium is higher than that for hydrogen because there are two protons in the nucleus. The nuclear charge is greater, so the pull of the outer electron is larger. More energy will be needed to pull an electron out of the atom. Coming to the lithium, this atom has the three protons. So we would expect the pull of electrons to be greater. However, the first ionization of lithium is lower than that of helium because the filled inner shells exert an shielding effect which lowers the effective nuclear pull, and hence we can conclude further away from the nucleus will be lower nuclear attraction for an electron, and hence there will be a smaller ionization enthalpy. And coming to the next effect, that is the penetration effect. The shape of the orbital also affect or influences the ionization energy. The ionization energy corresponding to the removal of an electron from a given energy level varies in the order S, P, D, F, and this can be explained as follows. The S electron here, so, in their motion around the nucleus, have greater probability of coming closer to the nucleus than the PDF electron of the same principal energy shell. In other words, S electron penetrate more towards the nucleus than the P electron, and the penetrating power of the electrons in the uh, given principal energy level varies as S greater than the P, P is greater than the D followed by the F. Thus the S electrons experience more attraction from the nucleus than the P, D and F electrons of the same principal energy shell. It follows, therefore, that the energy required for pulling out an S electron is maximum and it decreases in pulling out of a p electron and d electron or an f electron of the same principal energy shell in the order. So we may say that S followed by P followed by D and F. So the ionization energy corresponding to the elimination of an electron for a given energy level varies in the order as greater, followed by the P, which is lower than the S, followed by the D, which is lesser than the P, followed by the F, which is lesser than the D electron. Coming to the applications of the ionization enthalpy. So the first application of the ionization enthalpy is the to explain the trend from the metallic to the non-metallic characters of an element from left to right in a period. So metallic or electro-positive character of element increases as the value of the ionization enthalpy decreases. Hence, metallic character of an element can be predicted with the help of ionization values. As we move from the left of the periodic table, we may find the elements have the low ionization potential value. Therefore, they form the ionic bonding by losing the electron, which is a typical metallic. From left to right, the ionization value increases and the tendency of the elements to lose the electron is decreased and therefore they are less reactive. So at the end of the period, elements have very high ionization energy and they are not ready to take up electrons and form, and hence they are typically non-metals. So the metallic and the non-metallic character can be predicted with the help of the ionization value. The same is also true with the p block element. So the electropositive character is coordinated with the ionization value. So the s block elements are metals, and here the yellow color represents the metalloids, that is in between the metals and the non-metals, and the blue color gives the nature, that is they are non-metal. And the second is the relative reactivity of the metal increases with the decrease in the ionization value. The ionization values of the first and the second group metals are comparatively low, so they are more reactive. The ionization values of inert gases are very high, so they are almost unreactive. But this is with the exception with the highly electronegative element, which has a higher ionization potential. Still, they are highly reactive. So this is only with the this can be given correlation only with the electropositive elements. And the next thing is to determine the number of valence electron in an atom. So we can find out the number of valence electrons by knowing the ionization potential. For example, the lithium has the first ionization energy 520, second 7300 kilojoules per mole, and the third to be 11,750 respectively. This value shows that removal of one electron is very easy, and from the lithium, which clearly says it has only one valence electron in, or only one electron is present in the valence shell. And the next is the reducing power of an element increases as the value of the ionization decreases, because tendency to lose the electron increases. So lower the value of the ionization energy, the greater is the reducing power, because easily electrons can be removed as expected by the oxidizing agent, and hence they are highly reducing in nature. From left to right in the periodic table, the reducing power of the elements decreases, but down the group, the reducing power of the element increases. And coming to the variation of ionization enthalpy in the periodic table, and the following is the periodic trend in the ionization energy or observed. So when we look at this chart from left to right across the period, the ionization enthalpy increases and down the group the ionization energy decreases. And along the period, the ionization enthalpy increases from left to right. And this has been seen in the earlier picture. So let us look for the reason why is it so. The above variation can be explained as follows. On moving across a period, the atomic size decreases, the nuclear charge increases, and therefore the force of attraction exerted by the force of attraction exerted by the nucleus on electron in the outermost shell increases. Consequently, it becomes difficult to remove an electron from the outer shell of the atom, and hence the ionization energy increases. So the ionization energy will be a maximum for the noble gas which has the stable electronic configuration NS2 NP6 configuration. But there are certain variation in the ionization energy along the period is not smooth. Some irregularities are distinctly observed. This is due to the fact the atomic size is not the only factor which determines the ionization energy. The variation of the ionization energy increases with the atomic number has been depicted in the earlier shows. So when we look at this, the ionization energy when we compare to the hydrogen to the helium, helium has a higher ionization because of the completely filled s orbital. So when we take the electronic configuration or compare the electronic configuration of beryllium and nitrogen, the beryllium and nitrogen have the slightly higher ionization energy because of completely filled subshell, that is S subshell in the case of beryllium, and half filled p orbital in the case of the nitrogen. So the electronic configuration of when we take the boron, it is 1s2, 2s2, p1. So here, if here by removing one electron, that is from the p1, the electronic configuration get converted to the completely filled orbital, and hence it is very easy to remove an electron from the boron, and hence the ionization potential is lower compared to the beryllium where the ionization energy is slightly higher because of the field S subshell. The same is also true with the nitrogen and the oxygen. So here we expect the oxygen to have more ionization energy with respect to the trend, but the nitrogen experience more ionization potential because of the half-filled subshell. And when we take the uh, neon, that is the inert gases, because of the completely filled NS2 NP6 or octet configuration, the ionization energy is very high. And coming to the explanation, that is the trend of the ionization energy along the group. In general, down the group, the ionization enthalpy decreases. And this is very much clear from this figure. On moving down the group, the nuclear charge increases. There is a gradual increase in the atomic size due to the increase in the number of shells, a number of the shell, that is the principal energy shell. There is a increase in the number of inner electron which shields the valence electron from the nucleus. The overall effect of increase in atomic size and the shielding effect is much more than the overall effect of increase in nuclear charge. Consequently, the outermost electron is less and less tightly held to the nucleus as we move down the group. Hence, the ionization energy decreases as we move down the group from the top to bottom. For example, when we take the group, lithium has the highest energy, that is the ionization energy compared to the cesium. So this is the trend across down the group. And coming to the session summary, in this video we have defined what is the ionization enthalpy and what are the successive ionization enthalpy and what are the factors that are going to affect the ionization enthalpy like the atomic size, the electronic configuration, the nuclear charge, the number of electrons in the inner shell as well as the penetration and the application of ionization which give an indication about the nature, metals, non-metals, reducing power and about the reactivity and also the number of electron in the valence shell. And we also learned the variation in a group where the ionization energy decreases and in a period it increases along with few abnormalities. Also, we have looked across the period. And these are the references for this topic. Thank you.